Hi, this is Math 1350, and this video is over section 10.3, which is going to be on geometric sequences. A geometric sequence is formed by multiplying the same number to each term to create the next term. And so instead of adding the same number like in arithmetic sequences, we're multiplying the same number, or you're multiplying by a kind of percentage in a sense. So we have what's called a common ratio that we distinguish when we're finding a geometric sequence. So it takes the form for the nth term of a sub n is a sub 1, your first term, times r times n minus 1. Right, and so let's say we have numbers between two numbers in a geometric sequence. In this next sequence we have we're going to look at the 6 geometric means between 11 and 4808. Right, and so basically we have to find a number that is multiplying the first term to the next term to the next term until you get to 1408 by the 8th term. So this is when n equals 1, 2, 3, 4, 5, 6, 7, and 8. And so we can write this out using this formula. 1408 is the first term 11 times r, some value that we don't know yet, to 8 minus 1. And so 1408 over 11 is equal to r to the 7th. And 1408 divided by 11 is 128. So 128 equals r to the 7th, and so we take the 7th root and we get 2. So r equals 2. And so we're multiplying 2 to every term. So 2 times 11 is 22, then 22 times 2 is 44, then 88, then 88 times 2 is 176, and that times 2 is 352, and that times 2 is 704, and 704 times 2 is 1408. Alright, so if we look at the partial sum, it has a formula, just like the partial sum for arithmetic, this partial sum for geometric, as we add up all these different numbers. And so it's a sub 1 times 1 minus r to the n over 1 minus r. Right, and so if we are looking at here the partial sum for the first six terms of the summation 3 over 4 to the k. Okay, now we can rewrite this as summation from 1 to infinity of 3 times 1 over 4 to the k. And then we can even rewrite this again as 3 times 1 over 4 to the k, since 1 to the k is always 1. Okay, now we gotta go one step further. We want to rewrite this as k goes from 1 to infinity. My summation signs are getting bad. 3. Now I'm going to write this as 1 over 4 times 1 over 4 k minus 1. Right, so I took one of those away from the 1/4 to the k. This way I have that -1, which is what we need for this geometric sequence. And so now our a sub 1 is going to be equal to the number in front of this, 3/4. Our r is going to be equal to 1/4. And so our summation for 6 terms is going to be 3/4, 1 minus 1/4 to the 6th power over 1 minus 1/4. And let's do some simplifying here. 3/4 on the bottom as well. 1 minus 1/4 to the 6th power. Okay, so we'll have 1 minus 1/4 to the 6th power. It's just 4096. And so this will find our common denominator. So 4096 over 4096, that's your 1, minus 1/4096 is 4095 over 4096. Which as a decimal, it's going to be really close to 1. 0.9998. Okay, so some things about geometric sequences and series. If r, and we're just talking the absolute value of r, if r is less than 1, so a half, a fourth, something like that, then r sub n converges to 0. Right? And if r is absolute value of r is greater than 1, then r sub n diverges. And so summation of 1/3 to the n, 1/3 is less than 1. And so there is going to be a convergence, and so it's going to converge through a certain number. And then for the summation of 6 to the n, 6 is greater than 1, so it's going to diverge, which means that you won't get a summation for this when it goes to infinity, and it's going to just increase without bound. Now, when a series that's infinite does converge, right, as the summation for this follows a sub 1 over 1 minus r. Okay, and so in this next case here, r is greater than, well, I'll write it this way, r is equal to 2. So r is greater than 1. So the series does not converge. In the next one, your r is equal to 2/3. So there we do have a series that converges. So series converges. A sub 1 here equals 7. R is equal to 2/3. I already wrote that. And so your summation here is going to be 7 over 1 minus 2/3, which is going to be 7 over 1/3, which is going to be equal to 21. So if we come up here, we said the sum is 0.5, come up here to 1/3, and put it down here. We're finding this summation. A sub 1 equals 1/3, and so we would have 1/3, and R equals 1/3. 1/3 over 1 minus 1/3, which is going to be 1/3 over 2/3, which is 1/2. Okay, and so that's how we get that 1/2 here. All right. So this next question is going to be an interesting one. We're going to rewrite the repeating decimal as a fraction in simplest form. So 14.26 repeating. So 2.26, 26, 26, and so on. And the way we're going to do this is create a sequence out of it. So we'll have 14 plus 0.26 plus 0.0026 plus 0.000026, and so on. Each time for these, we're multiplying this by 0.01, and that's how it moves over, and that's what we're adding to it. So A1 is going to start out at 0.26. Alright, and so again, we're not worrying about this 14 here right now. We're just worrying about this sequence here from 0.26 plus 0.0026 and so on. So the summation here for this infinite series is 0.26 over 1 minus 0.01. Okay, which we'll write as 0.26 over 0.99. I'm going to get this as a fraction, 26 over 99. And so that's the summation of all those infinite 0.26s as we go through. Okay. And now to get the total summation of this, we'll add the 14 back in. So 14 plus 26 over 99. So let's make 14 with the same denominator. So we'll have 1386 plus 26 over 99. So add 26. We get 1412 over 99. And when we divide 1412 by 99, we get our 14.26 repeating. Alright, so a company is investing in a marketing campaign that is expected to increase its customer base geometrically. In the first month, the company acquires 100 new customers. The customer base is projected to grow by 20% each month. Right, and so we're going to write a formula for this. A sub n equals 100 times 0.2 for the 20% to n minus 1. How many new customers will the company acquire in the 6th month? So we'll plug in 6 for n. So 0.2 to 6 minus 1. So we'll do 100 times 0.2 to the 5th. Oh, I see. This is not 0.2. This is 1.2. We have to add this. So it's adding up. So it's increasing. So let's we write this 100 times 1.2 to the fifth. And so we get about 248.8. 8 or 249, almost 249. Okay. What will be the total number of new customers acquired after 6 months? And so this is s to the sixth. And so we don't use this formula. This is for infinite. We have to use this formula here. That's your partial. And so a sub 1 is 100 times 1 minus 1.2 to the sixth over 1 minus 1.2. Right, so 1.2 to the sixth. So 1 minus that divided by 1 minus 1.2, and put parentheses around here. Okay, and then times 100. And we get 992.99, so about 993. Engineers designing a new type of LED that increases its brightness geometrically over time. The initial brightness of the LED is measured at 50 lumens, and the brightness is expected to double every 3 hours. Right, so with it doubling, R equals 2. And so we'll have A sub n equals, it's going to start at 50. And then we're going from, all right, this way, R to the nth. So it's doubling. So if n is 1 and R is 2, then that gets you to 100. So we'll have to adjust this. So we have actually, hold on a second. Let me think about this. First month is 50. It's doubling every 3 hours. So we're starting out at 50. In 3 hours, it should be 100, which means we need that to be a 1. Let me define my ends here. In 3 hours, this is n minus 1. So at 0 hours, we're at n equals 0. All right, and so when we write this as 52 to the n, we're at, when we put in 1, we get 100. All right, and so we want to make this 50 times 2 to the n minus 1, which is going to be 100 2 to the n minus 1, right? Because we want that n minus 1 to be the exponent, so we have a geometric sequence. Alright, so that's our A sub n. Now we want to know what would the brightness be of the LED after 12 hours. Well, this, if you divide this by 3, this is n equals 4. Right, so 3 is 1, 6 is 2, 9 is 3, 12 will be n equals 4. And so a to the fourth is going to be 100 times 2, 4 minus 1. It's going to be 100 times 2 to the third. which is going to be 100 times 8, which is 800. Alright, so that is the end of our chapter on sequences. I think the last chapter we're going to do is chapter 7, and we'll get into systems. Alright, I'll see you then. Bye.